Hi, welcome to Hard-Boiled Synthesis, lecture 16. I gotta keep track of this stuff. Today I'm just gonna summarize the outcomes of calculating effect sizes for the catnip repellency studies. I'm gonna talk a little bit about what I had to do to get a nice data set of effects and add a few things to my wall of deviations from best practices, because in order to get this data set, I had to overlook a bunch of stuff that I would normally spend more time to curate. I would normally spend more time to try to squeeze out as much information as I could. I didn't spend much time, didn't spend as much detailed approaches to extract the effect sizes. All right, well, first things first, let's go to my Excel sheet. And if you remember from the last effect size lecture, I was showing you guys how to calculate Hedge's D effect sizes based on the raw data, the means, standard deviations, and sample sizes. I've done that all already. Let me bring it up for me. And I had about 270 aspirational outcomes that could potentially have been converted into effect sizes. Now, after having converted everything to an effect, I lost about 50 outcomes. And there were many reasons why I wasn't able to compute an effect size from those outcomes. The most common one was standard deviations or some other measure of variability like a standard errors or variances or even ranges, interquartile ranges. If that stuff is missing, then there's really not much you could do to compute an effect directly. And in my case, I did not spend time trying to figure out ways to address those gaps. And so all those study outcomes that were missing standard deviations, they had a mean, they had a sample size, they just end up getting dropped. And that's a real bummer. That's like 50 outcomes that could have been useful to explore heterogeneity amongst repellency studies. But I had to drop because the studies reporting these outcomes inadequately did not provide enough information for me to do this. And the usual suspect was a figure, like a bar graph, and then no error bars with that graph. No error bars around whatever measure is being reported in the bar graph. And there's no way you could, unless you had access to the raw data, there's no way you could recover those data. Now, the ideal mark, the usual mark, the way I approach these missing gaps is I would probably impute them. And imputation methods are becoming more popular now for meta-analysis. Impute means filling in a gap, right? So we're missing a bunch of standard deviations. We're going to fill those in with something. And there's soft and hard imputation approaches. The hard, and I don't mean like hard as in complex, difficult to understand. I mean hard as in rigid. You create a number to impute, to fill in the gap, and then you don't touch it again. That's a hard imputation. A soft imputation tries to address some of the error associated with imputing, filling in the gaps. And so what you would do is fill in all the gaps, do a meta-analysis, and then fill in all the gaps again randomly, repeat the analysis, fill in all the gaps, repeat the analysis. You know where I'm going with this, right? And so you repeat it over and over again, and then you take an aggregate view of all those analyses, and cooked into it is the error associated with imputing information. Those models can get fairly complicated. I mean, there's a million ways to impute information, especially standard deviations. There must be like 20 ways out there to fill in missing standard deviations. Some are based on hard or soft approaches. These don't get used a lot. And my impression is because there's two reasons. One is if you're using the soft imputation approaches, you're essentially modeling data and filling in gaps. And that could distract from the outcome you want to talk about in your study, right? So now all of a sudden a big chunk of your study is describing this modeling technique to fill in gaps. That might distract the reader quite a bit in trying to evaluate what you found with your synthesis. Another problem is a lot of people kind of feel iffy about imputation approaches. Basically, you're generating data to address the gaps, and that generation, that creation of data, some people are like, ooh, no, you're just cooking up data and trying to do analyses with made up data. And maybe that is very true if you're imputing like a huge block of missing information in your studies. Like if more than half of your studies are missing standard deviations, and then you model data to impute that missingness, I could see why someone is like, wait a second, what's going on here? You're not doing this right. And the imputation methods are useful when you don't have that many to impute. And in my case, I had 50 outcomes that would have needed some imputation, some rule to fill in the gaps. And I feel like that's too much. That might have been too much. I mean, I don't know what 50 out of 200 or so would be, like one fourth. Yeah. 25% missingness is too much to stomach to start imputing stuff. And so maybe, it's a real bummer. You're dropping a lot of information. Right. I'm flat out dropping 50 outcomes because they're missing standard deviations. But hopefully I have enough studies and I was able to collect enough heterogeneity across those studies that then missingness was not a big deal. Now, missingness can happen in many different ways. It could be random. It could be non-random. Non-random missingness is the worst. People aren't reporting the standard deviations or the variability in their outcomes because they're trying to hide something, right? Outcomes were super variable. Standard deviations, standard errors were very broad. Confidence intervals were very broad. Just don't report those things. And then nobody's going to be like, ooh, your study's a little funny here. Why is there so much error associated with these outcomes? I don't think people are doing that in these repellency studies. There's a lot of reasons why we plot things, and best practices, if you follow those, you would include errors on your bar plots, especially if they're means of something. But sometimes you don't. I mean, a lot of these were older studies. The guidelines on how to report information weren't quite straightforward. There certainly were best practices back then, but no reviewer may not pick on, hey, you didn't put error bars on your means. You didn't report standard deviations on the means you reported in your tables, right? Especially when you have like many means to report, it's easy to overlook reporting the variability associated with those means. Now, I don't think you can get away with that, but back then, it happens. And again, just to emphasize one of my points is meta-analysts are historians of the stats reporting practices of a discipline, and it's easy to quickly determine that, oh man, things were very different 30 years ago, 35 years ago. in terms of what is reported and what it's not. I guess the example with the repellency stuff is like the study, the raison d'etre of catnip by oh no, what's his name? Tom Eisner, right? Like his experiment wasn't really like a real experiment. He just said, this is what I think he did. You know, he was looking at light traps at night. He had a big sheet and he like shoved catnip in the faces of the things that were hanging on the sheet. And if they flew away or not, he would write down whether or not they were repelled by catnip. I mean, that's not a super convincing way to provide evidence of repellency. But that was, you know, back in the 60s. You know, even the stats hadn't caught up at that point to be able to do a proper analysis with that. ANOVA and all those things were around t-tests, but ecologists, I don't know, weren't really, I don't know if they were super statsy at that point, right? That's really early in our development. That'd be something cool to look into. Anyway, back to the effect sizes. Let me jump into here. Okay, so I was talking about missingness imputation, so this becomes one of the part of my wall of deviations from best practices, part of extractions. Did not impute missing standard did not impute missing standard deviations. I feel if you're missing few standard deviations, then look into these imputation methods. You know, they'll address gaps and it'll just, you know, you went the extra effort to keep some effects. So here's just another item that I add to my list of things that I normally do, but I didn't do this time because I'm so behind in this project. Okay, I need to focus. All I wanted to do today was talk about the effect sizes. Okay, so in total, I got about, I started with 270 aspirational outcomes. I was able to calculate 226 effect sizes from those, right? So again, about 50 I had to drop because they were missing standard deviations. Another issue is a bunch of these outcomes were not reported as means. Let me jump into PowerPoint here. Not reported as means, right? Just a contrast between catnip effects and a control effects, right? This is what I wanted to find in most studies, but instead they reported as counts. And what is clear with the repellency studies is a lot of people are measuring counts, right? Number of mosquitoes repelled, number of mosquitoes landing, number of mosquitoes biting, number of mosquitoes attracted. But then they do funny stuff with the counts afterwards. They convert the counts into percent protective efficacy or percent repellency. What they're doing there is calculating an effect size. And all the studies that reported counts that way, there was no way for me to retrieve raw data from that whatsoever because they're already represented in an effect. And that effect, there's no way to rearrange it to back calculate the original counts. But many other studies do report the raw counts. What do you do with raw counts? This becomes like a chi-square problem, like in this table right here. You have number of mosquito repelled by catnip versus the number not repelled, the number repelled by DEET, the number not repelled by DEET. And from that, you calculate a log odds ratio. And this is a fairly famous effect size. Like this is the bread and butter of medicine right here. Synthesis medicine, it's all about odds ratios. They really have strict, standardized experimental designs, randomized control trials. The outcomes of those are meant to be unambiguous, right? So it's either it worked or it did not. And that's what you're counting. The times that it worked and the times that it didn't. And for example, does a vaccine work or not? You count. And then you convert that into an odds ratio, and then you're able to assess whether or not there's like a positive effect, a negative effect of the treatment. And the beauty of the odds ratio is that it's very well understood, right? It's a highly studied metric. There's a ton of research just on the odd ratio itself. And you could do all sorts of neat things with it, convert it to percentages and that. And this is what I really feel like repellency researchers need to use instead of percent efficacy, protection efficacy, percent repellency. Everyone's using different equations with these counts. This is what you need to use. This is what we need to start using as a discipline to report repellency effects, is through odds ratios. They're just so versatile. The equation seems odd, but there's a beautiful derivation to it. It has a known variance. And I think the one layer that's missing with percent protection, percent repellency is, what do you do once you've calculated the percent repellency? I mean, most studies take it a step further and do analyses with the percent repellency stuff. And there's no guidelines on how to properly analyze those repellency metrics. We don't understand their distributional properties. And so everyone's kind of doing t-tests, ANOVAs on percent repellency or percent protective effectiveness. But you can't use those conventional stats with those metrics. Log odds ratio, we have a whole suite of stats associated with log odds ratios that allows you to do proper statistics with the metric, right? So that's an additional layer of logs odds, an advantage that it has over all these other mosquito repellency metrics that just seem like all over the place, is we know how to analyze odds ratios. We don't know how to analyze percent protective efficacy. It's just like a mishmash of acrobatics with counts. Avoid all that stuff by using things that we know about for like 50 years. We've been using log odds ratios, more than that. Super well studied. Now you say, hey Mark, one of the lectures you were like, avoid ratios at all costs. This is different. This is a ratio based on counts, okay? The ratio I was criticizing before was a ratio based on means. That's just a mess, but it counts. The properties are very different. And feel free to explore the log odds ratio literature on like how to analyze this stuff. It's so well documented and there's so much information out there that I feel this would solve so many problems with the plant repellency research, is if everyone just kind of used this metric. But alas, everyone just kind of uses their own thing and everyone seems happy about it. And then I come along and I'm like, I'm trying to synthesize all these outcomes and everyone's reporting things in a different way. I mean, why aren't we trying to be consistent here? Okay, so back to the Excel. And so the majority of outcomes that I extracted were Hedge's D, but a bunch were in odds ratio. So like study 156, all these effects were represented as odds ratios, as counts. So that's what this stuff is right here. Right, you got 4 numbers, 4 counts, and then you convert that into an odds ratio. Now you're probably asking yourself right now, hey, those counts are like, they have fractions, they're not complete integers. What's going on here? That's some of the variability associated with extracting data from plots. A lot of these things are reported as percentages, and then you have a total sample size, and you're left to kind of convert that sample size with the percentage to get raw numbers. You're going to get really small fractions. Does that mess up the odds ratio? Not really. It doesn't. Like, I could have spent time to, like, clearly this is supposed to be a 12, and this is supposed to be a 44, but I have slight differences between the two because of the way I had to extract data from a graphical, from an image. That doesn't really impact the effect here too much, not at a measurable level. Like, I could change it right now, right? So here the effect is 0.3749, and now it's a 0.3750, right? So the fraction was so different, not too different. I prefer to keep the original whatever number I extracted from the plot rather than rounding it up or rounding it down. That's just an additional layer you have to talk about in your paper, that you rounded the counts. I didn't. It doesn't really break any rules. And so in total, I think in terms of odds ratios, let me just stay focused here. In terms of odds ratios estimated from the paper, let's do a quick count of how many we'll just count all these. I'm sure there's a quicker way to do this, but I'm in Excel. I mean, I'm not working under optimal conditions to begin with. Log odds ratio. So out of the 226, 90 about 39% were log odds ratios. Maybe a more conventional meta-analyst would have totally dropped everything where you could not have computed a Hedge's D directly. But I make the effort to at least try to pull out effects, especially when I know I could convert back and forth. And is there a trade-off to conversion? Yes. Converting a log's odds ratio into a Hedge's D, it's an approximation. It's not a perfect conversion, right? So you may be slightly adding some noise to your effect sizes. And so this is where sensitivity analyses, I'm not in the meta-analysis part yet, but this is where sensitivity analyses come in, where you try to you do analyses based on what you think are methodological issues with your data. And so here, once I get to the meta-analysis point, I will do a comparison between the Hedge's D effect sizes and the Hedge's Ds that originated from odds ratios, just to make sure that they don't differ. They have similar variability. And so the odds ratio derived Hedge's Ds are not introducing variability in my synthesis. And so overall, okay, so 2 more things before I end today's lecture is, let me have a drink here. I added some columns here that you didn't see last time. Right, so I already added a source column, which will allow me to do my comparison, my sensitivity comparison between Hedge's D and then the Hedge's D, which were converted from odds ratios. And then I have this new column called Sine. Now the sine column is something I use to change the direction of the effect. Now that seems like a little abstract thing to say, but when you have your effect sizes, you're fairly standardized in the way you represent the outcomes. You got your treatment group, catnip, and you have your control group, DEET. But these are reported as different responses. So number of landings, percent landings, average landings, time to land, right? These have things that are different units, different ways to measure a repellency effect. But sometimes they're reported as an inverse response or a complement to a response. Classic one of this, and the easiest one for you guys to understand, is mortality. Okay, a researcher may decide to report their findings as the number dead. Okay, number that died in the treatment group, the number that died in the control group. For our repellency studies, the number repelled versus those that weren't repelled. The complement to that would be to report survivorship instead of mortality. So the number that survived in the treatment group and the number that survived in the control group. And that means the effect is going to be in the opposite direction. If there's high mortality in the treatment group, you're going to get a positive effect. But if you have high survivorship in the treatment group, you're also going to get a positive effect. But you need to convert things in a common currency. Everything has to be reported in terms of like a mortality effect or a repellency effect. So a study may report like number attracted as opposed to number repelled, right? It's the opposite thing. And so you need to change the sign of the effect to account for these different reporting practices. And so there were a bunch of studies that reported things that were different from typical measures of repellency. They will report things that are the opposite measures of repellency. So instead of reporting things of number of, in terms of average number of mosquitoes landing on an arm, they report the average number of mosquitoes not landing on an arm. Or some other thing. So it's the effect is still good. It's just the way it was reported, it's in the opposite direction than what you need. And so I always reserve a column where I have to change the sign of the effect. So here I had to change the sign of the effect because let's see if I can find a good one here. That's not many studies needed to change the sign of the effect. But the worst case scenario is you don't pay attention to that and you start doing your analyses, and what you're doing is you're mixing positives and negatives effects together, which really can completely destroy any synthesis outcome from that, because things aren't really quite comparable and you're not aware of it. And so I like to give a good pass over all my effects to make sure that they're in the right direction conceptually. That if, say for example, I was looking at mortality effects, everything that was reported as survivorship effects would get their sign inversed, their sign changed, so that everything becomes a mortality effect again. Okay, I think I talked enough about this. So really what's next for us is to start analyze these things with meta-analysis. And we're finally getting into it. I think by the end of the week, we'll be done. We'll have the final question answered. Is catnip 10 times more effective than DEET? We'll know. We'll know real soon. I'm excited. Okay, I talked enough today. If you have any suggestions on how to improve the class, put a message. I will try to respond. I've been pretty bad with responding to messages. I will respond. And thank you very much for watching. Next lecture, maybe I'll answer the question. All right. Take it easy.